Thanks. Okay, my video is rolling, so if you don't be quiet, people are going to think that I run a terrible class. People on YouTube, they'll say mean things. I do get, people do subscribe, although I know you're being sarcastic. Okay, so energy number 7. A billiard ball rolls down a ramp that's 1/2 meter high. That's the ramp, and the cool thing about energy is you don't need to know, under the conditions where this is useful, you don't need to know anything about the shape of the path. This is number 7, so that would be a weird one to start with if we were doing all of them, but there were solutions? Okay. That sounds about right. I don't remember exactly. Okay, so this is 1/2 meter. And so this billiard ball starts up here, rolls down. It has a mass of 0.15 kilograms. And then apparently this is in a universe where billiard balls have different masses. So this one down here is because to indicate that the shape of the path does not matter at all in this problem. Yeah, if your table looks like that, you don't have a good table. So that is one of the key reasons that this energy method is useful in some problems, is if the only work is done by conservative forces, you don't care at all about the path. You just care about the beginning and end points. At the bottom, it runs into the second one. So the questions are, first, what's the velocity of the first ball? So let's call that one M1 and this one M2. So what's V1 right before the collision? And second, what are the velocities after the collision? Yeah, so it's starting at the top at rest, and so the first thing that you really should do, the simplicity of the problems that we tend to do makes you sort of careless about this, but you should verify that there isn't going to be any work done by non-conservative forces. And if there is work by non-conservative forces, those have to be included, and you have, via like the work energy principle. So let's draw a free body diagram and think about what forces are acting as it rolls down the ramp. Well, we're assuming that this is a particle, and so for particles, things where we're ignoring the like the length dimensions, we're just going to have a normal force and a weight force. And so conservative forces, do we have any? Yep. And then non-conservative forces? Normal, but the good news is the normal never does any work. So that means we can use the conservation of mechanical energy, and I'm going to set it up as instant 1, instant 2, instant 1 is at the top of the hill. At the top of the hill, what's the speed? 0, so this is 1/2 times 0.15 times 0 squared equals 0. There's two instants. So for the conservation of energy, we're dealing with the rolling of the ball down the hill. So the two instants are at the top of the hill with no speed and at the bottom of the hill with no height. You know, we're going to call this our height equals 0. So what's the potential energy at the top of the hill? We have the mass, 0.15 times 9.81 times the height. And if our height equals 0 is at the bottom of the hill, this is 0.5. And so we get 0. No, don't tell me. 0.14. So that's 7.3 355, something like that, right? What? 0.15 times that is 1, yes. I'm just checking to see if your calculator works. Okay, it does. 358. Okay. And at instant 2, what do we know about the kinetic energy? So 1/2 times 0.25 times v1 squared, that's the speed we're trying to find. So 0.125. Nope. Yeah. Sorry. Okay. And then what's the potential energy at the bottom of the hill? Yeah, so 0.15 times 9.81 times now the height is 0, so this is 0. Conservation of mechanical energy says 0 plus 0.7358 is equal to 0.075 v1 squared plus 0. And so what's v1? Yes. So it's the total mechanical energy at instant 1 is equal to the total mechanical energy at instant 2. And what do you get for v1? Something around that, right? Okay. And then it asks for a velocity vector, so then you'd have to choose a coordinate system and find a vector with that magnitude in that coordinate system. By the way, one thing to keep in mind about this, notice, we did this calculation as if that ball was sliding. So if the ball slid down that ramp, it does. And so if it rolls down, then you have to take into account, so that potential energy doesn't just turn into kinetic energy of the center of mass moving, which is what we're measuring here. Some of that energy also goes into making it spin. And the harder something is to make spin, the more energy goes into that rotation. And so what we did, is actually an overestimate the speed at the bottom of the hill. Have any of you seen the demonstration that they at least used to have at the Science Museum, where you have a ramp and you have all these different rolling shapes and you try to guess which one's going to get to the bottom first if you roll like a sphere against a disc against a hollow piece of a pipe or something? And there are differences in how fast they go, even though the masses are the same. Something that's sliding without friction would be going faster at the bottom of the hill than anything rolling. And so we'll talk about that. We'll get to that in the next topic when we talk about rigid bodies and changes of orientation. When you're treating something as a particle, we don't really have any way to deal with that because we don't deal with changes in orientation yet. So this will be dealt with when we talk about rigid bodies. Okay, but now we have our estimate for the speed of the first ball at the bottom. So now we're going to do the collision. And if we think of a view from above, just because that's the most foolproof way to think about collision calculations. And here's our coordinate system. And we have the first ball moving like this with a speed of 3.13 meters per second. And it's running into the second ball. So this is M1, this is M2. What are the velocities after the collision? The first thing we have to ask ourselves is what kind of collision? So how do you want to treat this, as an elastic or an inelastic collision? Inelastic, they would stick together. Pool balls are almost perfectly elastic. So yeah, you want to because it's easier, but that doesn't give very good answers with billiard balls. You know, they're designed to be as close to elastic as possible. Imagine what pool would be like if the cue ball stuck to whatever you. That's true. You'd scratch on every shot. So it's an elastic collision because they bounce. Oh yeah, that's true. Billiards is different. Okay, so all of the motion is going to be in the x direction. So let's use first conservation of linear momentum. And that says that before the collision, we have a mass of 0.15 and an x velocity component. This is only in the x direction. An x component of velocity of positive 3.13. And before the collision, the mass m2 is not moving. Then after the collision, this is 0.15. After the collision, we have the mass of 0.15 times v1 plus the mass of 0.25 times v2. What's 3.13 times 0.15? What? 47, okay. And then divide, so 0.4695 or whatever, divide by 0.15 so we can get the V1 by itself. Oh yeah, you are. Okay, so this is 5/3. Okay, so 3.13 minus 1.6 repeating times V2. Okay, that's our first equation. Everybody with me on that? We're going to substitute this into the conservation of kinetic energy. Nope. No, this is different. This is conservation of linear momentum because we're dealing with the collision now. And so with collisions, you're always going to do conservation of linear momentum. Since it's an elastic collision, we're also using the conservation of kinetic energy, which is different from the conservation of mechanical energy. But since we're substituting this into, well, let me take this off. Since we're substituting this into the conservation of kinetic energy where everything's squared, we might as well just square this right now. So V1 squared is equal to, what's 3.13 squared? G? Yeah, pretty close. Square root of G, was it? How did I calculate what? The momentums? Yeah, the total momentum. So that's what we did here. This is in the x direction because there's no y components. This is the momentum before the collision of mass 1.
So that's what you calculated up there. A, 2.13.
Yeah. Right. So this is the mass times the x component of the velocity. The second mass isn't moving before the collision. And then after the collision, mass times velocity plus mass times velocity.
Gotcha.
Cool. And what's 3.13 times 2 times 3.13 times 1.6 repeating? I'm just trying to FOIL this out. 10.44 V2, And then what's 1.6 repeating squared? What? 25/9 V2 squared. Okay. So let's call this equation star. This is the one we're going to really substitute in. And then conservation of kinetic energy. Says 1/2 times the mass of the first one times the speed of the first one before the collision squared plus the kinetic energy of the second one before the collision is equal to 1/2 times 0.15 times V1 squared plus 1/2 times 0.25 times V2 squared. Let's divide everything by 1/2 and 0.15. So this goes to 1.6 repeating. And we have 9.81 is equal to all of the stuff from equation star, 9.81 minus 10.44 V2 plus 2.7 repeating V2 squared plus 1.6 repeating times V2 squared. The G's cancel out, and we get that 0 is equal to what's 2.7 repeating plus 1.6 repeating? 4.4 repeating times V2 squared plus 10.4. Yeah, I think you're probably right. It would have been easier if I would have kept it all fractions. Now we can factor out the 4.4 repeating V2. So this is V2 minus what's 10.44 divided by 4.4 repeating? 2.35. Just 2.35. And the two roots are 0 and 2.35. This is what's happening before the collision, so we don't want that one, so we want this one. And then V1, we can plug that back into this equation. So 3.13 minus 1.6 repeating times 2.35, what do you get? Negative 0.78. Okay, can you say anything intuitively about the fact that after this collision, V2 is moving a little slower than V1 was moving before the collision, and V1 is moving backwards? Yeah, so if you think about the relationship between this collision and the, what did you say that's called, Newton's cradle? Yeah. The collision thing, the desk thing. If they had the exact same masses, what would you expect those to be doing after an elastic collision? So if V1 comes in at 3.13, when they hit, think of what happens with that desk thing. This one stops dead, and this one takes off at the initial speed. So if they had the same mass, V2 would be 3.13, V1 would be 0. If V1 was more massive, then V2 would be moving forward faster than 3.13, and V1 would be moving forward slowly. And in the case that we have, where V2 is more massive, V2 is moving forward slower than 3.13, and V1 is moving backwards. So for elastic collisions, where one of the things starts out at rest, you can always use that Newton's cradle intuition to sort of make sense out of your answer. Okay. Any other homework questions? Yeah. Yeah, so that's why I squared. So I used conservation of linear momentum, got this expression for V1, squared it just because I knew a V1 squared was coming in the next equation, and then I substituted the right side in for V1 squared.
What's the other equation we use to find the one happen?
So the one says, yes. So conservation of kinetic energy says 1/2 m1 v1 squared plus 1/2 m2 v2 squared. It can keep going on if you have more two bodies before the collision is equal to 1/2 m1 v1 squared plus 1/2 m2 v2 squared. Keep going through all the masses after. And this is only used in elastic collisions, which is why, you know, if you had your choice, you'd rather deal with inelastic collisions. Those are, the math is a little simpler. Intuitively, it's not really any more complicated. Okay, number 9. Does an object gain or lose gravitational potential energy as it moves higher and lower? Yep. Okay, so well, the answer to this just comes from the formula for gravitational potential energy. But there's something more important about this question than just that equation. There's an important intuition here. So gravitational potential energy is mgh. And so if an object goes higher, gravitational potential energy increases. And if an object goes lower, gravitational potential energy decreases. And this is actually, this gets at an important thing to sort of intuitively understand about potential energy. Important intuition about potential energy in general. if an object starts at rest, in a potential energy field, the force applied by that potential energy, because potential energy is a way of getting at a force that's applied to things. So the force applied by the potential energy let's not say tries, pushes the object this is notes you need to know for life. The force applied by the potential energy field pushes the object toward lower potential energy. Okay, so what that's saying, yes. Okay, so get that in your notes and then let me know when you're ready for more. That's what I've been waiting for. All right, so lower potential energy due to gravity is down, higher is up, right? Which way is the gravitational force trying to push an object? Down. So the gravitational potential energy is always trying to push things towards a lower potential energy. Okay, that's what a potential energy field does, always. Yes? Yeah, that's right. So if you start with potential energy, and well, if all you have is potential energy, then if you go to a lower total potential energy, the speed increases because you're exchanging that for kinetic energy. Yeah. Okay, so let's think about it in terms of springs now. This is number 10. Does a spring force have greater or lower potential energy, spring potential energy? I guess really we should say an object attached to a spring. Have greater or lower spring potential energy as first the spring gets farther from its resting length, or two closer to its resting length. So again, mathematically, the answer to this just comes from the, yeah. Okay. Mathematically, the answer just comes from the formula for spring potential energy. The spring potential energy is 1/2 times K times X squared, where X is the distance from the resting length. So what's the answer? Does that potential energy get higher or lower as you pull or push a spring farther from its resting length? Potential energy gets higher. If you return the spring to the resting length, it gets lower. Okay. So now think of what happens if you pull an object away from the spring's resting length and start it from rest. Where is that thing going to go if the only force is a spring force? It's going to go back towards the resting length, and actually it would get there going too fast, go past, and then you get oscillation. But that spring force is always pushing it towards lower spring potential energy. Okay? Yeah, that's right. Right. Objects don't like potential energy. Although, I like. Good. Good. Then I won't objectify you. I guess that's all I have to say about that. But remember that potential energy fields are a way of describing forces. Potential energy fields are force fields. And those forces are always pointing towards lower values of potential energy. Okay, that doesn't mean that the object always goes to lower potential energy, because there can be other forces acting. Like obviously things can go up, and that's raising their gravitational potential energy. It goes up if I hold it up, but gravity is trying to make it go to a lower potential energy. Something like that is going to be on the quiz. Okay. All right, let's do another example. Let's take a 10-minute break, come back at 8:48, and then I'll have you work on some problems. Okay, so here's the problem I want you to work on together at the board. So you have two carts at the bottom of a hill. And then you have this hill. First cart has a mass of 1 kilogram. The second cart has a mass of 0.5 kilograms. Before the collision, this one's moving at 5 meters per second. And the question is, how far will the half kilogram cart get up the hill? And we're talking about just a vertical distance. After an elastic collision. Okay, so go to the board and see if you can through that. Yeah, just tell them to contact me. But if you talk during my class, the deal's off. Okay, so the way this works is there are two parts of this problem. There's a collision, and then after the collision, this part, well, both of them have velocities, and then it's conservation of energy just to take the starting velocity of this and figure out how high up this hill it goes before its velocity is zero. So part one is the collision. And that's an elastic collision. And so you use conservation of linear momentum in the x direction says the mass of the first one times its velocity before the collision. Remember, these are vector components, so you have to take the signs into account, but this is moving in the positive x direction. Plus the momentum of the second one, which is at rest before the collision, is equal to 1 times the velocity of part 1 after the collision, plus 0.5 times the velocity of the second one after the collision. And you get V1 is equal to 5 minus 0.5 V2. This is where some of you had trouble going from this to this. It'll come back. Okay, and then conservation of kinetic energy is the second one. So that says 1/2 times the mass of the first one times its speed squared plus kinetic energy of the second one is equal to 1/2 times 1 V1 squared plus 1/2 times 0.5 V2 squared. No, this is, yeah, that's right. And if you combine these, you get that V2 after the collision is 6.6 repeating meters per second. And then part 2 is cart 2 rolling up the ramp. If you think about a free body diagram of cart 2 as it rolls, there's a weight and there's a normal force. This one's conservative. This one's non-conservative, but does zero work. So we can use conservation of mechanical energy at instant 1 and instant 2. The kinetic energy at instant 1, this is cart 2, so that's 1/2 times the mass of 0.5 times its velocity at the start of the roll. So that's after the collision. That's 6.6 repeating squared. We'll call, for this part, we'll call the bottom of the hill h equals 0. And then the potential energy at instant 1 is 0. At instant 2, the kinetic energy is 1/2 times 0.5 times, we're going to the highest point that this object gets. So the speed at the highest point right before it starts coming back down is 0. So the kinetic energy is 0. The potential energy is the mass times 9.81 times the height, and so that's 4.905 h. And so we get, I don't know, whatever this is, 0.25 times 6.6 repeating squared plus 0 is equal to 0 plus 4.905 h. And so that final height that it rolls to is, I think it was 2.26 meters. Any questions about that? So let's do another one. It's sort of the same idea. But let's say that there's a big mass hanging on a cable. Let's say that this is 2 kilograms. And a bullet is shot into this block. The bullet has a mass of it's okay, it's made for this, 0.005 kilograms. That's 5 grams. And this bullet is shot into the mass, at which point the mass swings up to highest point of 0.75 meters. Long enough that it can do that without. It doesn't matter because there are 2 forces acting, the weight and a centripetal force from the cable, and that doesn't do any work. Okay, so what was the speed of the bullet? You're right, it sticks in the mass. And this is an inelastic collision. This is actually, like before high-speed video and stuff, this was how people measured the speed that a gun fired a bullet. This is called a ballistic pendulum.
Oh, yeah.
Yeah. That's the only way to fight off the tyranny of the potato overlord. So go to the board and see if you can work through this.